Now we start to learn in chapter 18 about concentration distribution in solids and in laminar flow. Yeah, so we have learned in the previous video, we have learned how what is fixed flow, the uh, the the idea what is fixed flow, and also what is combined mass flux. And now we try to solve the problems in chapter 18. You can see that there's some 8 examples, and I'm gonna explain the uh, sub chapter 1 and 2. Okay, let's open your burst book and then let's see in chapter 18. Right, so okay, again in burst book in transfer phenomena, in chapter 2 in momentum transfer we saw how a number of steady state viscous flow problems can be set up and by solve and making a shell momentum balance. In chapter 9 in heat transfer we also have learned how we can make a shell energy balance to solve problems in steady state heat conduction. For this case, we will formulate it problems about on steady state diffusion problems using shell mass balance. Okay, the procedure is the same, if virtually the same as used previously. So if you have learned well in momentum transfer or in heat transfer, you can also do well in mass transfer. Usually the mass balance is made over a thin shell perpendicular. Yeah, it should be perpendicular to the direction of the mass transfer. So this shell would be cut off the direction of the mass transport, because what we will calculate here is the mass flux, which the mass rate or the concentration rate divided by the cross-sectional area. So and then the shell balance will lead into the first order differential equation, which may be solved to get the mass flux distribution. Into the expression, we can insert the relation between the mass flux and the concentration gradient in fixed flow, or in, let's say, the combined mass flux, like we learn in N, what is the uh, uh, correlation as N, and also correlation with J, for example, and also what is correlation with the concentration gradient, and that will result in a second order differential equation for concentration profile. With that, we by putting into the boundary condition, we can use integration constants. The integration constant that appear by in the resulting expression will be determined by boundary condition, and then later on we can see the concentration profiles or the mass flux profile. Remember, concentration profile is defined with C, or for molar concentration, or rho for mass concentration, and mass flux is defined with small n for mass flux, or molar flux is used for capital N. Right. So in chapter 17, we point out there is a relationship between a combined flux and molecular flux and convective flux. So in here it's written again. So NAZ, which is the combined flux of A in direction of Z, equal to JAZ, or this is in this case written with minus concentration, mixture concentration, multiplied with DAB, multiplied with the fraction gradient, mole fraction gradient, divided with its dou distance, plus its convective flux distribution, XA multiplied with NAZ plus NBZ. So to use this equation, we have to know the relationship with B and A. Yeah, so this only can be done if something known beforehand with the ratio of NB and NAZ. Let's say NA, for example, the solute, yeah, or the small part. B is usually the remaining B component in the mixture. Okay, so in each boundary, diffusion will begin to specifying this ratio by physical and chemical reasoning. Right. Okay, I'm just gonna skip these sides and I'm gonna see the shell balance boundary conditions. Yeah, in shell mass balance, the rate of mass in minus rate mass out plus the rate of production of mass A by homogeneous reaction, of course, the summation will be 0. So the typical boundary condition that we can learn usually first the concentration at the surface usually can be specified. For example, XA equal to XA0, or usually the mass flux at the surface also can be specified. For example, the mass flux, the combined mass flux of A at the surface equal to Na0, or if we know the ratio of concentration gradient, concentration ratio of Nb and Na is known, we can know also the concentration gradient. If the diffusion occurring in a solid at the solid surface, where the solid surface A is close to surrounding stream, we can usually the relation can be NaO equal to a constant multiplied with its driving force, yeah, which NaO is the molar flux at the surface, CaO is the surface concentration, CaB is the concentration of A at the bulk field stream, and Kc is the mass transfer coefficient. Yeah. Okay, so or if there is a chemical reaction, we can also appear, let's say, just assume as a first order chemical reaction. So we can say the NaO equal to its chemical reaction constant multiply with the concentration, where K1 dash dash equal to B first order chemical rate coefficient. Okay, now let's see chapter 11.2 about diffusion of stagnant film. You can see here. So we have, let's say, there's a liquid A. There is a circle tube here, and because of diffusion, some of the liquid A will vaporize and just travel to up there, and where in here and it will meet a gas stream of A and B. Okay, so liquid A is evaporating into gas B. Yeah, we imagine there is some defined to maintain liquid level should be just similar as Z equal to Z1. And this is just written Z equal to Z2. So the cross-sectional area is gonna be the when we're gonna slice up this control volume to with the thickness of delta Z. So these are gonna be our control volume. Okay, so this is Na. Na is traveling. So how about Nb? There is no Nb here, yeah, so there is no mass flux of B that traveling in this case, because B is not stagnant. So and we can call Nb equal to 0. Yeah, so if you go back to this case here, for the diffusion in stagnant film, the combined flux Na is the molecular flux. This is the convective flux. The one that moving is only A. Yeah, and B we can call it Nb equal to 0 for this case. Right? Go back. So, okay. So let's say we have XA1, which is the vapor pressure of A divided by the total pressure. Yeah, this is we have the boundary condition XA1, and here we have XA 0, XA2. Yes, so this is this is the concentration of XA1, and this is the concentration of XA2. Yeah. Okay. So if we know that there is a net flow gas upward from the liquid gas interface, and the gas velocity as the cylinder will be smaller than in the center of the tube. So for to simplify the problem, we neglect the effect and assume there is no dependence of z component of the velocity in the radial coordinate. Now, because of B is stationary, so we can conclude that NB is 0. So when NB is 0, the molar flux will be given with NB equal to 0, and then we will get this equation. Try it by yourself. Try to put it by yourself. The equation in the 18.1. Where NAZ, if we put NB equal to 0, this is gonna be the equation of NAZ, a function of concentration. Yeah, so now we start to putting into steady state mass balance. This is the cross-sectional area, NAZ at Z minus cross-sectional area, multiply that NAZ at Z plus delta Z, we divide it, and then taking limit delta Z equal to 0, that become minus dAZ over dZ. So this is the profile, the differential equation for mass flux of A. If you want to put the solving NAZ, a function of concentration, you can put it these sides into the equation of 18.2 strip 4. You put it here, and then you end up with a second order derivative, and then if you do integral one time, that become a constant, and a second integration will become ln, and with a function of there is two constant, and you can put both of them the boundary condition in the concentration. For example, at z equal to 1, xa equal to x1, z equal to z2, xa equal to x2. So when you put all the constant into these equations, you end up with this type of equation. Yeah, and if you try to plot this one here, that's gonna be in the graph. This is gonna be the concentration profile, where this is the concentration profile of A, and this is gonna be the concentration profile of B. Right? So by using mass balance, mass shell balance, we can see we can get also A, and also we can get profile for B obtained by 1 minus XA. Right, so we can also calculate the XB average using this equation or this area. So the average value of XB is usually the logarithmic mean of the terminal concentration. Alright, so I hope you can understand step by step about this shell mass balance to solve the mass transfer problem to get the profiles of the concentration because of the mass transfer.